Hi, let's remind you what we have done already and what we will be doing next. So we were examining sequential circuit analysis. In this first frame, that means previous video, we have seen the classification of sequential circuits, Moore and Millie machines. Why we have done this classification? Because there are some differences between Moore and Millie machine sequential circuit analysis. Therefore, we have seen this classification. And then next, in this frame, what will we be doing is to examine to analyze Moore machines. So there are two examples here. The first one here, I'm not going to go in the details of these Moore machine analysis, but I'm going to talk about why this Moore machine is. So rather than analysis, I would like to deal with definition of the Moore machine and the differentiation between Moore and Millie machine. At the beginning, I am going to show you this. So I'm going to leave the analysis of this circuit to you. The information is available here. The next example, Moore machine example 2, I will be doing the analysis step by step for this example. Let me to go in the details of this circuit now. So that is a Moore machine. So I'm going to switch to another open board. As you know, I've got to do the transfer now. Open board, here open board. Okay. Now that's the circuit. Now we are saying this is a Moore machine. So just remind you what Moore machine is. The output functions are the functions only the independent variables x1, xn and y1, small y1, yr. So this is in general output function of a sequential circuit. Now if this is Millie machine. So if it is Moore, then z is the function of y's only, y1, yr. Then it is Moore. If it is like that, then it is Millie. The difference is Millie, in addition to state variables, Millie machine has got input variables as well in the z functions, output functions that is. When you come to the Moore, there is no input variables included in the output functions, only the state variables. Now you've got to pay attention these variables. These are the independent variables. So altogether, these and all of those are independent variables. So you never see double y's here. Small y's you're going to see. These are the small y's, not the capital y's. So that is the critical point, because capital y's are dependent variables. So capital y's, g functions, are the function of x1, xn, y1, yr. So this should not be seen here. So let's come to our circuit now. What is our input variable? That's x, is my input variable. And my output is this Z. So if you look at this Z output, is also this next states and present states. So which one I am going to choose it? I'm going to write it y1, y2, not capital Y1, capital Y2. So then, according to this definition here, my Z functions are the function of the state variables only. Therefore, this is a Moore machine. Now, analysis of this circuit, I'm not going to show it. I'm not going to take this example in order to show an example for the Moore machine analysis. So the circuit that I prefer for analyzing is this one. So in the presentation, that is the second example. So this one is whether it is Moore or not. Let's check it. How we are going to check it? If you look at this Z output here, is the function of y1 and also y2, isn't it? This is y1, this is y2. So yz is equal y1 times y2. Since the z is the function of state variables only, once again, I would like to remind you, these y's are the small y's, not the capital Y's. Small y's are the present state variables. Capital Y's are dependent variables, and it is next state functions relation, dependent variable, and it is a next state function. Okay. Now, if you look at this, our circuit now, it's got one input, and this input is X, and I've got one output, and this output is Z. Since I've got two memory elements, that means I've got two state variables, y1 and y2. So two state variables, and variables, let me write it, and the number of states 0, 0, 1, 1, 0, 1, 1. So 4 states we've got for this circuit, this sequential circuit, I can say that. And this is a Moore machine. Now, how I am going to analyze this circuit? This circuit is given to us. First, we're going to find a mathematical model. And then we're going to find state table. And then last but not least is state diagram. You might ask why we've got three models, since the function of these models are the same. That means if you know one of the model, you can find the other model. Why we call the model? Model means the behavior of this circuit. If you've got a model of this circuit, you do not need to know this circuit. This model, by using this model, if you give me an input sequence, I can find out the output sequence, either by using the mathematical model or the state table or the state diagram. I could do that. So why we are giving three? Because in some cases one of them is beneficial to the other one. So why one of them is beneficial to the other one in some cases, I will be explaining this at the end of this video, because after you've seen our explanation, it is easy to understand. So let's find the mathematical model first. So mathematical model has got output functions, and next state functions we're going to write. So output function is this. Since it is just one, it is this. We finished that. So the next is to find out, let me clear this area a bit. Next state functions. There are two of them. One of them is y1, the other one is y2. These two functions should be function of the independent variables. What are those independent variables? This small x, y1 and y2. So these are the independent variables. So the first thing you do, you're going to write the definition relation of this T-type memory element. T-type memory element definition relation, I can show it to you on this diagram. 0, 1, 0, 1, 1, 0. So the corresponding function, so inside we've got capital Y, so this is T prime time Y plus T time Y prime. So that means these are the product terms corresponding to this one, and this is this one. Okay, so if I write now, how I'm going to write this too? There are two memory elements. So for this first one, I'm going to write T1 prime Y1 plus T1 itself Y1 prime. Why I put these one indices here? Because this is related with the first memory element. For the second memory element, it is going to be like that. Y2 and T2 Y2 prime. So these are the next state functions, but these are not the ones that I am dealing with. Why is that? I said already, this function must have these independent variables only. In here I have got T1 here, T2, T3 here, which is not the independent variable as you see here. So I've got to transfer those T variables to independent variables. So let me just mark them up. So I'm going to replace those functions. How I'm going to do it is easy. T1 prime, let's come, this is T1, and that is, okay, that's T1. So T1 is x time, so this is x, and this is y2, x, y2, isn't it? X, y2 is T1, so prime of it, multiplied y1 plus T1 itself, x, y2 that is, multiplied y1 prime. So if you open it now, so this is, if you use the Morgan theorem, so it's going to be x prime time y1 plus y1 y2 prime. So what I am saying that is here is x prime plus y2 prime. That is the Morgan theorem that I used. Plus, I change the order now, x, y1 prime, y2. So let's come to this one. T2 is equal directly x, isn't it? So it's going to be x prime y2 plus x y2 prime. That's y2. So this is the mathematical model. So if I put them in a group here, these three functions are make a mathematical model, that model. So once you know the mathematical model, then you can draw the state table. State table, in order to draw the state table, means you transfer these functions to a kernel map. So this kernel map has got the functions of three variables. Why it is three variables? Here you are. We've got three variables here, three independent variables here. So in order three variable kernel map, it's going to be something like that. y1 and y2 are the state variables 0, 0, 0, 1, 1, 1, 1, 0, and x is 0, 1 here. So normally, inside I'm going to write capital Y1, this function, and Y2. I'm going to write those two functions on the same kernel map. When you come to that Z, I am going to write a column, a separate column for this Z. I'll explain why I am going to write this like that. As you see here, since this machine is a Moore machine, a Z function depends on the state variables only. That means these variables independent from X. So I can show the result as one column here. So I can directly transfer the Z function in here, multiplication of those two. So multiplication 0, 0, 0, that is 0, that's 1, and that's 0. Inside, I'm going to write y1 and y2 functions. So if it were milli machine, I was going to write y1, y2 and put a comma. After that, write the z output function next to it, not as a separate column like this. That's the difference. When you come to that milli machine, you're going to observe that. Now how I'm going to transfer y1 from the function to the diagram is easy. So if you look at this term now, this is a product term. This product term has got all the variables. That means 1, 0, 1. X is 1, y1 is 0, y2 is 1. So if I put 1 here, that is that term. So this term here is this term here. It includes just 1, 1 because there is no any variable which is deleted or disappeared. So if you look at this one now, y1 is 1, y2 is 0, 1, 0, that's that row, isn't it? So for this row, I'm going to put 2 1s, meaning that x1 variable disappears. If you consider this one and this one, only the x variable values are changing, so this variable is going to disappear. What is left is going to be y1, 1, y2, 0, which is this. So if you consider these two ones, this is a first order subcube. Corresponding product term is this. So I'll make it a mark on that. So this product term means this one and this one. What about this product term? This is x prime y11. X prime means 0. y11 is those two. So I'm going to put this. If you consider this 2, 1, this 2, 1 is a first order subcube. Corresponding product term is this. So make it a different color now. Put a blue one, blue color. So this one and this one both makes this product term. So that product term that is. Okay. So what about the other cells here? It's going to be 0. So I considered all the product terms, so all the other cells are going to have 0 value. So that is y1, capital Y1 is transferred to a kernel map. And if you consider the other one now, let me make it a black color. So y2 function has got two product terms. One of them is x prime y2. X prime is this column, y2 1 1 is here. So one here, another one here, what has disappeared? This y1 variable, because the value of y1 variable is changing, so this disappears, and y2, since it is 1, this is 1, and x prime. So this 1 and this 1 comes from this product term. So the other product term is x1 but y2 prime. x1 is this column, y2 prime is those two rows, so first and fourth. So that means I'm going to put one here, another one here, and put two nodes, two node and two nodes here. So this 2, 1 is related with this. So the others are going to be 0 because I finished all the product terms. So what I have done with this black here, this is, let's make it a proper one. So that is y2. Now this is a state table. So if you know the state table, you could analyze this circuit. So the last one, so we have done this one as well. The last one is the state diagram. Once you know the state table, it is easy to find the state diagram. Let me draw it here. So we've got 4 states. So one of them is this 0, 0, 0, 0. The other one is 0, 1. And here 1, 0. And here 1, 1. These are the states, right? So we are at a point now to differentiate Moore machine from the Millie machine. Since Z output function depends on the state variables only, I can write the output value just underneath these state variable values. Multiplication of those two, 0. Multiplication of those two, because the function is y1 times y2, it is 0. And that is 0. And that is 1. So this, what I have done here, I have transferred this Z function here to my state diagram. So what is left to transfer this side? So it says if your present state is 0 and your input is 0, yet your next state is 0, 0. That means you stay in the same state. So turns itself for the input 0. When the input is 1, your next state is 0, 1. If your present state is 0, if you apply 1, you come to next state, 0, 1, if the input is 1. So second line here, if your present state is 0, 1, that means you are here. If you apply 0, you come back to that present state again. Your next state and the present state are the same, isn't it? 0, 1 present state, 0, 1 next state. When the input is 0. When the input is 1, present state is 0, 1. Your input is 1, your next state is 1, 0. So it's going to be like that. So we finished this line as well. Let's come to this line. Your present state is 1, 1. If you apply 0, your next state is 1, 1. So it comes back on it. 0 input. If the input is 1, you go back to 0, 0 state. When the x1 is applied, you go back to 0, 0. From present state 1, 1, go to 0, 0 when the input 1. Present state is 1, 1. When the input is 1, your next state is 0, 0, as we have done here. So the last one is 1, 0 state. If you apply 0, it goes back to itself when the input is 0. When the input is 1, your next state is 1, 1. So this is the state diagram. Now what we have done up to now is to find out three models for a given circuit: mathematical model, state table, and state diagram. Now these models are ready now to do the analysis for any given input sequence. So if somebody gives you any input sequence, example, here you are, let's say x, and time axis is like that, 0, 1, 0, 1. So that means you're applying this input starting from 0, so that's T0. If I put that way, if that way arrow, so this one comes first. So in here, that 0 comes first. So I am saying now, if somebody gives you a bit stream like that, I can easily give you the output sequence. That means that sequence. That is analysis, isn't it? So in order to find the output for a given input, I must give the initial state as well, because you are going to apply this input sequence, yes, but what is my present state? Am I going to apply it for this present state, or this, or this, or this? So if none of the initial state is given, that means there are 4 corresponding output sequences for the same input sequence. You might call it bit stream, input sequence, or the input train, pulse train. Okay. So let's assume our present state is y1, y2 is 1, 1, and apply this input. What's going to be the output? That is the question. Now I've got to remind you a few things. So there is no limitation about the length of the bit stream. So we've got 4 pulses applied here, but it could be 16 or it could be any number. So that means this input sequence is independent. For any input sequence, I can find the output by using the same models. So that means when the input sequence is changing, these models are not changing. They are there. We will be using the same models for any bit stream input analysis. So let's go inside the details of this analysis. Let's come to this. Oh, okay, so sorry. So let's do this now. Which color? Let me use a different color, that blue color. So my present state is 1, so I will start from the last one. So the easiest model, that's the point now I could explain to you. Although there are 3 alternative models here, the best model for us now to do is this state diagram. So you're going to see we can write the output sequence easily. So look at this. Your present is, so this is what you're going to observe. If your present state is 1, 1, you're going to observe this first, isn't it? So I'm going to put small 1 here. If it is 0, when the clock pulse comes, you're going to observe this one once again. So second, this again. So if we apply 0, and then if you apply 1, so that means you're going to apply this one, your Z output is going to be 0, isn't it? So that's the third thing that you're going to observe. Sorry. Now, so that is the one that I applied here. That's that one. So apply that 0. I am in here in this state now. Apply 0. So I'm going to observe that Z output once more. So it's going to be 4th output that I am going to observe. When I apply 1, so that's going to be the 5th one that I'm going to observe, because this diagram tells me if my present state is 0, 0, if I apply 1, my next state is going to be this one. When my next state is this one, so my output is this. So if I write this, what I have seen here in the order now, 1, 1, 0, 0, 3, 4, and 5, which is 0. So this is what I am going to observe. This bit stream has got 4 bits, but I've got 5 bits here. The first one is the one corresponding to the initial state. When I am in the initial state, this is I'm going to observe at the output. And then 4 clock pulses, I'm going to observe this at the output. So that is easy to do now. If you want to do this analysis on the state diagram, so I'm going to show it to you, so it's going to be more confusing. Why is that? So my present state 1, 1, so we're going to start from here. So that means this is what you're going to observe first. So if you apply 0, when you apply 0, your next state is going to be this one, isn't it? So you're not going to observe this, of course, this Z output I am talking about. So let me correct the mistake that I have done here. So delete this one here. So that's the first thing I am going to observe, what I said, for the initial state. When I apply 0 and your present state is you apply 0, when the clock pulse comes, your next state is this. So once again, you're going to see this output because you're on the same line. So your present state is 1, 1 now. After you apply 0, your present state 1, 1 again. Then for this present state, you're going to apply 1. So this one now. Present state 1, 1, you apply 1. Your next state is 0, 0. So your next state is 0, 0. That means this state, isn't it? So for this, you're going to observe this 3 times. So when you come to that 0 state, you're going to apply input 0. So you're going to apply 0. So your next state is going to be 0. So that means you're going to see that once again. Now your next state is 0, 1. For the next input, that's going to be present state. That means this state. And you're going to apply 1. So that's that one. Your next state is 0, 1. When it is 0, 1, multiplication of those two is 0. So it's going to be the fifth one. So if I write the output now, 1, 1, 0, 0, 0, which is the same as this. So the difference between this one and this one, you're going to find the next state for an input. Then for the next input, your previous input next state is going to be present state. So think about what I said, then you could understand it much better. So that is the second approach, and the last one is this one. So mathematically we're going to do it. So how I'm going to show you how we're going to do calculation for the first one only. Let me check this. So Z is 0 is the multiplication of y1 and y2. So multiplication of those two, Z. So that's true. From here I can say that. So how I'm going to check the output for this now? For this input I'm going to examine. So this is 1, 1. Present state 1, 1. So Z is output is 1. 1, 1. Output is 1. So in this function it is 1. So present state 1, 1, you apply 0. So that means now I'm going to, what I am saying here, y1, y2, 1, 1, and x is 0. What's going to be my next state? So x0 means that is 0, isn't it? Prime of it is 1. y1 is 1. You're going to get 1 here. So capital Y1 value is going to be 1, isn't it? Capital Y1 value is going to be 1 here. Capital Y2 So x is equal to 0, prime of it is 1, y2 is 1, so that's going to be 1. I'm not going to look at this one. 1 plus anything gives you 1. So that's 1. Okay? So I found this output and I found the next function, next state here. So for the next input to come to for this one, I'm going to consider this 1 as present state once again, because for the previous input, that means 0 input, my next state is 1. For this next input 1, this my next state is going to be present state. So it happens here as step by step. So for each input and present state, you're going to calculate these three functions. So it is a cumbersome to do this. Then conclusion is this. If you are doing the analysis of a given small circuit, like here, the best model to be used is state diagram. If your circuit is complicated, then the state diagram is going to be more complicated indeed. That means to draw the state diagram takes quite a long time first. Instead of doing this, you could use this mathematical model. So for the complex circuits, the mathematical model is good for computer calculation. So this model is the best model for a complex computer-related calculation. If your circuit is small and if you're going to do the analysis by hand, the state diagram is the best one. That's why we are seeing different models, right? The next step, so in here, in this analysis, we don't see any time at all. So in reality, how this time introduced, we use time diagram. That's the time diagram. Now in this diagram, we are going to see all the variables, how they change with respect to time. So the top independent variable is time. So how I'm going to do it? So I'm going to draw the x first. Okay. That is x input. That's time axis. So in this one it was 0. In the previous one it was 0, 1, 0, 1 again. Now this x is time. So that's t, that's xt. Okay. Now the next thing that I'm going to draw with respect to time is going to be pulses, clock pulses. Clock. So let's write clock. So for each input, I must have a clock pulse. Why I need that? Because otherwise, if there is no clock for each input, that means that if there is no pulse, that means this input is not accepted by the circuit. As you know, the clock pulse means my memory elements works. If the clock pulse is 0, there is no clock pulse at all. That means this input is not accepted by the circuit. So therefore, I have got to put a clock pulse for each input. So let me write these inputs 0, 1, 0, 1. So I'm going to put here, oh sorry, this clock pulse here, another clock pulse for input 1, another clock pulse for input 0, and another clock pulse for input 1. Okay, so if you look at our circuit, so there is a small circle here. That means negative edge sensitive, isn't it? So that means my sequential circuit will work on this edge because of that circle that I showed you already. So it says our present state is 1, 1, which is this one. So I'm going to put y1 and y2 here. And z. So what I am saying is this now. Up to now, these are external input and clock. These are inputs. And these are going to be capital Y1, capital Y2, and Z functions. So this is the mathematical model related graphs. So the first one, second one, third one, and that is small y1, capital Y1. As you know, small y1 and capital Y1 is going to be observed on the same wire. So what is the difference? Y1 is going to be observed first, and then capital Y1 is going to be examined next. So this is Y2, capital Y2, and that is Z. So from that, what it says, our present state is 1, 1 before the first clock pulse comes. So let me make it this. So my circuit, sequential circuit, is going to work on this edge. Maybe throw this down. Maybe and this edge. This is not straight line. I made a mistake, but I can correct it now. Let me correct it now. Okay. Now, before the first clock pulse, my initial state I am going to observe. My initial state is 1, 1. So small y is 1, small y is 1, 1, 1. Now I can, afterwards I will be using this state. Now I am in here. I haven't applied any clock pulse at all. I'm going to observe that 0 here, which is make it a different color. So 0 here. So I can draw the other z values because z is equal to y1 and y2. So once I found this, multiplications I am going to write here for this 1, 0. So the next state, 1, 1, if you apply 0, my next state is the same, isn't it? When you present state 1, 1, you apply 0, you come back to that. So my next state is 1, 1 again. So this is going to be continue until the next clock pulse negative edge comes. So that's 1, 1. So I am in this state now, and I'm going to apply 1. So you see here on that edge, this is where you accept the input. So for this edge, you accept this input 1. So present state is 1, 1. Your input is 1. Your next state is 0, 0. So my next state is going to be 0, 0. So my present state now is 0, 0 for this pulse. For this pulse, it is. For this pulse, this is the next state. For this pulse, this is the present state. Now 0, 0 state, and you are applying 0. And it says here no change, because if your present state is 0, if you apply 0, you come back to 0. So your next state is 0, 0, 0. So your present state is 0 now. You're going to apply 1. So that's that one. So that means negative edge, you accept this 1. So your next state is 0, 1. So that's going to be 0, and that's going to be 1. So this is how the state variables are changing here, and multiplication of these variables is going to give me why I put 0 here. I shouldn't have done this. I made a mistake. I will correct my mistake. You see, z function is y1 times y2. So 1, 1, 1 is going to be 1. And this multiplication 1, 1, 1, multiplication 1, 1, 1, multiplication 0, 0, 0, multiplication 0, 0, 0, and multiplication 0, 1, 0. So that's the output. Now this diagram is very important. Why is that? As you see, the time is included here. So this is xt changing with time, that's clock is changing with time, and this is y1 and y2 values changing with time, y1 and y2. Oh, sorry, it should have been time t. These are all independent variable, top independent variable, let's say t, t, and t. How z output function is changing in terms of time, how y1, y2 changing in terms of time. Okay, so the result that we have seen here is the same as we have found here, isn't it? So this one is the state diagram, includes time in it. This one is the output bit stream. There's no time included here. So that has got more information because it shows you which time what change is going to happen. So that's the end of this video then.